Alright, set operations. What are they? They are ways in which we can combine two different sets to create a new one. So let's start with an example. Our first set operation is the union. So what happens if we take the union of two different sets? How does that work to create a new set? So for example, if we have the set that contains 1, 2, and 3 and another set which contains 3, 4, and 5, what is the union between these two sets? Well, what a union does is it basically tells you to combine the contents of each of these sets and use it to fill up the new set. So our new set will just be a mashup of the previous sets. So it will contain 1, 2, 3, 4, and 5. That's it. Now notice we have a repetition of 3. You see it appears in this set and this set, but we don't repeat the 3's in our new set. The key here is we don't want repetitions in our sets at all, because repetitions are meaningless. We don't have to consider them. They're not important for this context when we're learning set theory. Alright, our next set operation is the intersection. It is denoted by this upside down U sign. So what do you do with the intersection between two sets? Well, let's use the same example as the previous one. We have 1, 2, 3, and 3, 4, 5. The intersection between the two sets, what it does is it basically tells you to find which elements are repeated. So as you can see here, the element 3 is repeated in both sets. So once we have identified those elements, we use those elements that we have identified to create a new set. So this only has 3 because 3 is the only one that is repeated. So the intersection between this set and this set is the set which contains the number 3. Okay, that's easy enough. And again, we don't repeat the number 3. We have the number 3 once and twice, but we only put 1 inside of here. No repetitions. Okay, so what about the last one? We have 3 set operations, okay? This last one is called the takeaway operation, and it's denoted by this dash sign. So 1, 2, 3 dash 3, 4, 5 means the set 1, 2, 3 take away 3, 4, 5. So what do? We take away 3, 4, 5, but we can't really take away 4 because 4 is not part of this set. We can't take away 5 either. It's not part of this set as well. What we can do is we can take away 3 because 3 is right over here. So just take that away, and what are we left with? We're left with the set 1, 2. So this is what happens when you have 1, 2, 3 take away 3, 4, 5. Now, the important thing here to note is that this set operation, in this set operation, the order matters. So in the other ones, the intersection between two sets, it doesn't matter if you interchange it or not. Same with the union, but let's interchange things now. Let's have 3, 4, 5 on this side and 1, 2, 3 on the other side. Now what does this mean? This means 3, 4, 5 take away 1, 2, 3. We can't take away 1, it doesn't exist in the other set. We can't take away 2, it also doesn't exist, but we can take away 3. So let's do that, and what are we left with? We're left with 4, 5. So we see we arrive with different answers when we interchange this set and this set. So the meaning changes when we interchange the sets together, but we only have to worry about it when we're using this function. But when we're using another operation or function, then we don't have to worry about interchanging the two sets together. What we want to deal with next here is Venn diagrams. So Venn diagrams are a way to represent set operations or just, sets in general, but it's really helpful. We have two sets, which we'll call A and B, and our first set has the numbers 1, 2, and 3, while the other set contains the numbers 3, 4, and 5. This is how we represent set A, and set B. Set A contains 1, 2, and 3, while set B contains 3, 4, and 5. And this is easy to see. You see the numbers 3, 4, and 5, they're closed within this circle which we label as B, while the set A, which contains 1, 2, and 3, that's easy to see from here because the numbers 1, 2, and 3 are enclosed within the set A, or the circle A on this Venn diagram. Now the numbers 3 is repeated in both sets. That is why there is an overlap or an intersection between the two sets, which I have drawn over here, and we place whichever elements that happen to be in both sets within this area of intersection here. So that's how we represent sets with Venn diagrams. Alright, with this example in mind, let's try to visualize what a set operation will look like. What does A union B look like? Well, A union B is basically everything from A and everything from B, right? So the area that we're concerned about is basically all of this thing here, right here. And that's pretty easy to see, pretty easy to understand as well. So what about intersections? What do they look like? Well, we covered this earlier. So the intersection is this specific area over here, and it is the overlap between the two circles. So next, what about A take away B? A take away B, well, let's start with A. This is the set A. And what we have to do, we just take away B. So take away this part. Because remember, this whole area there is B. So just get rid of this intersection over there. So this is what A take away B looks like. Just A without the intersection. What about B take away A? Then that's just the same thing but on the other side. So we have B, but be careful to not insert the intersection. What we can do is we can also visualize complicated set operations with the Venn diagram. So what do I mean by complicated set operations? Well, what I mean by that is we can combine set operations like in a combo sort of fashion. So let's say we want to visualize A take away B union B take away A. So as you can see here, we are combining 3 set operations together, 1 union and 2 takeaways. So what does this look like? Well, A take away B is this thing which we have seen before, and B take away A is this thing. So it's basically just everything except for the middle part. Alright, what if we try a different combo of operations? What if we want A union B take away A intersect B? So this one contains each of the 3 set operations that we learned, all 3 of them, the union, the takeaway, and the intersection. What will this look like when we combine all of these together? Well, A union B is basically the entire thing over here, and we want to take away the intersection, and the intersection is the middle point. We take that away, and voila. You see, the Venn diagram for this thing over here and this thing over here are exactly equal to another. And since the Venn diagrams are equal, then they convey the same information. This combo of set operations is exactly the same and conveys the same meaning as this combo of set operations. So this is highly similar to equivalent statements, where we have one statement being equivalent to another statement even though they don't look alike with each other. So this just reinforces the connection between set theory and the language of logical statements. But we can do better than that. The connection, in fact, runs really deep, and we're going to try to explore that in this video. So earlier, in the last two videos, I think, we talked about if we have a set X such that P of X is true, then if Y is a part of that set, then this will be equivalent to saying P of Y. This guy on the left-hand side is equal to this guy on the right-hand side. If you need a refresher on why they are equal to one another, watch the videos before this one, the previous two videos. So now, why don't we make it so that Y is also an element of this set? Now we have Q of X instead of P of X, so these are two different statements. Then this will be equivalent to Q of Y, right? So let's see. I'm a bit lazy, so let's just rewrite this set. We're gonna call it as A. We're gonna compact everything down into a single letter, and we're gonna rewrite you as well, because you're long and complicated. We're gonna simplify you to just a single letter, B. So Y is part of the set A, and Y is also part of the set B. Okay. So in other words, we can say that Y is part of the union between A and B. Alright, so we have a translation for this guy. So we can translate that to logic, and we can translate this guy to logic as well. How do we translate this guy into the language of logic? Well, let's use a Venn diagram to aid our understanding. So let's just draw a small one over here. So we have A union B. Alright, let's think about this statement over here. Is this statement true? Is Y a part of A? Well, you can say maybe, right? Because I have a red dot over here, and that's going to be the possible locations for Y. So Y could be here, or here, or here, or here, or here. So let's ask the question, is Y in A? Is this statement the truth? Well, maybe, right? Because you see Y can be in A, but you can't say that with 100% certainty, because Y can also be in B as well. So is Y a part of A? Maybe. Okay. What about the bottom one? Is Y a part of B? Well, maybe. You also can't say for certain, because it could also be in A. So what do we gather from all of this? It's maybe in A or it's maybe in B. So it has to be in either of them. That's the best that we can say. We cannot say for certain individually, but we can say for certain that Y is either in A or in B. Okay, so since this guy over here is equivalent to this guy, and this guy is equivalent to this guy, can't we just write an OR in between these two guys as well? So what do we have? So we have P of Y or Q of Y. We can write that down in terms of logic. So P of Y or Q of Y. And I guess that's it. So we started with the assumption that we have A union B. That's this Venn diagram over here. And what we ended up with is the exact same statement, but in terms of logic. So that's good. We found a translation for union. We can translate union into set theory language. Okay, so how do we translate intersection now? Well, let's start with a Venn diagram for A intersect B. So we know that looks something like this. And I'm just gonna label up the areas that Y could potentially be in. So Y can be here, or here, or here, or here, or here. So notice this statement over here. Y is a part of A. Is it true? Well, can you say with 100% certainty now? Yeah, we can say with 100% certainty that Y is a part of A, because all the red dots are contained within the circle A. Similarly, all the red dots are also contained within the circle B. Both of these guys are true. Y is a part of A, and Y is a part of B. Alright, so let's do the same thing we did before. We put an AND statement over here, and we just write that down in terms of logic. So we have P of Y and Q of Y. So there we have it. That's the translation for intersection in terms of logic. Alright, we got one final guy to deal with. It's a takeaway B. Same as always, let's draw the Venn diagram. And let's draw the red dots. It could be over here, or over here, or over here. Could be in any of these places. Alright. So let's take a look at the statement. Y is a part of A. Well, that's certainly true. All the red dots are located within the circle A. What about Y is a part of B? Is Y a part of B? Well, B looks awfully empty, so that's not right. There are no red dots inside of B. So alright, we can work with this, right? So Y is not a part of B, so we can just slap a no sign here as well. But we know how to write that down in terms of logic. We just have to attach a not symbol in front of that, and then just combine things together like we did last time. So we have P of Y and not Q of Y. So yeah, I guess there we have it. This is the translation for A takeaway B in terms of logical statements. Alright, so these are our dictionary entries. This is how we translate set theory into logic. So as you can see, the connection is really deep. We can directly translate stuff. Alright, let's use this newfound knowledge, okay? So earlier I said somewhere in the beginning of the video that A union B takeaway A intersect B is equal to A takeaway B union B takeaway A. And we prove that with the Venn diagram. So the Venn diagram for these two are equal to each other, so we conclude that they are equal statements. So how else can we prove that? What if we want to do it without visuals? What if we want to explain the concept to, like, let's say a blind person who can't see a Venn diagram? How do we do that? Well, we're not entirely hopeless because we have logic, right? So what's the idea here? We can translate this in terms of logic, and we can build a logic table, and we can check whether or not the statements are equal by taking a look at their columns. If the columns are equal, then the statements are equal. We covered that in the equivalent statements video. So let's begin. So A union B is same as saying PY or QY. Now for this part, I'm just gonna make everything compact. So I'm gonna ignore the Y. I'm just gonna write P and Q. And I know this is not the proper notation, but we're lazy. We just want to make sure everything fits, okay? So we're gonna allow it for this special occasion. So we have not. Not is basically just this and this, right? And we have A intersect B, that is P and Q. So P and Q. That's it. So let's segregate this part over here and let's translate this guy. This guy is just P and not Q. And we union that together. So the union is an OR statement. And we just have to combine that with B takeaway A, which is Q and not P. Alright. So we can make a logic table now, and let's see whether or not they are equal. So let's fill in the statements for P and Q. What are our possible universes? Well, there's a universe where they're both true, a universe where they're both false, a universe where one of them is true and false. another universe where one of them is false and one of them is true. Let's fill in the statements for not P and not Q, because we're also going to need it. So this is just the opposite. So we have FT, FT, and over here we have F, TT, F. Right, so just the opposite. So let's begin. Q and not P, right? So these two guys. So that's the fourth fourth row. Only the fourth row satisfies both. So only the fourth row is true, while the rest of them are false. All right, what about this guy over here? This guy is P and not Q. So it's these two we're comparing. Let's check the rows. Well, in this case, it's the third row. The third row, both of them are true. So true here, while the rest, they don't satisfy the necessary conditions. They don't have enough truths. All right, so we have an OR statement, right? This is an OR statement. And an OR statement, we only need one truth. So this guy is true, this guy is true, this guy's false, this guy's false. So our final column should be FFTT. Let's see if it's equal to what we're gonna do on the other side. So we have P or Q. So P or Q. So only this guy, right? We only have to disqualify this guy because the rest have truths in them. So it's first one true, this one false, this one true, this one true. What about this guy? P and Q. So since it's an AND statement, that means only the first one is qualified. So we have true, false, false, false. But remember, we have a not symbol over here, meaning we have to flip what we already have. So that's just F, T, T, T. All right. So now all we have to do is combine them with an AND statement. So an AND statement means both of them should be true. This guy's true, this guy's true, so it's only in the third and fourth row. All right, only third and fourth row. So true, true, and the rest of you is false. So, hey, there we have it. This column is equivalent to this column, meaning this is equivalent to this, and meaning this is equivalent to this. So there we have it. We proved something from set theory without using a Venn diagram. So this is really good. I told you the connection runs deep. So now we can just get rid of visualization because sometimes that's difficult to do, and all we have to work with is logic. And I know this is a much lengthier process, but it's a much better one, okay? You don't want to be drawing Venn diagrams for, I don't know, 100 different statements. You would much rather work with a table. Alright, so that's it for this video. Thanks for watching.